All right, we're going to start with some basic ideas about probability. Now, one of the phrases I'm going to use a lot is we got to think like a statistician, which kind of is a little bit backwards. That sometimes it's a little bit weird, but that's partly the power of it. So, when we talk about hypothesis testing, we want to set up what we call a null hypothesis, which asks a kind of oddball question: how likely is it that I'm being fooled? Not how likely it is that I'm right, but how likely is it that I'm wrong? That is, what if there are actually no relationship there, and yet a person could be fooled into thinking there might actually be some pattern or relationship there? I understand, it's a little bit of thinking backwards. You're not trying to prove you're right, rather you're asking, how would you know if you were wrong? In the statistical testing apparatus, we distinguish the null hypothesis, which we often notate as H naught, from the alternative hypothesis, HA. We want to set rules how to distinguish if we're being fooled. We want to set out these rules even before we do the testing. In order to set up these rules, we have to have a good understanding of what actual randomness looks like. So let's start thinking a bit about randomness in the case of games, which, we all have the experience. If you've watched a game or played a game, sometimes the better player loses or the better team loses. There's just inherently randomness in the event. Frankly, otherwise, it's not very interesting. That randomness is kind of the point of why people play games or watch games. If there were no uncertainty about the outcome, then it's just a lot less fun to watch. Let's get a little bit more formal and say the team has a probability P of winning, and so there's a 1 minus P probability of losing. Keep it simple. We'll assume for now there's no ties, nothing else, just win or lose. We'll come back afterward and make it more complicated, but this is enough to start. So if they played 2 games, then we'd have the set of outcomes shown in the table here. The team could win game 1, those are the columns, and the team could win game 2, those are the rows. So the first outcome at the top left is if they win both games. The bottom right corner is if they lose both games. The off diagonals are where they win one and lose one. Either they win the first and lose the second, or lose the first and win the second. Now, one little bit of subtlety here. When we're writing out these probabilities, we're assuming these are unrelated outcomes. There's no such thing as streaks, or more precisely, there's no such thing as influence of streaks. A team might win 2 games in a row, but that does not necessarily mean they were more likely to win the second game after winning the first game, or vice versa. Now we can later test that hypothesis, look at the question: to what extent is that true in different sporting events? Sometimes that's called a hot hand in basketball games. People talk about that. If somebody sinks a bunch of shots, are they more or less likely to keep on sinking baskets? Answer: it's complicated. But anyway, having made that simplifying assumption here for now, don't worry about streaks. We can write out that notation. What's the likelihood or probability of 2 events, A or B, which we denote with that little upside down U sign? That's the intersection. What's the likelihood of A and B happening? Saying earlier, if A and B are independent, then one consequence is the likelihood of A and B happening is just the unconditional probability of A happening times the unconditional probability of B happening. In this case, if the probability of winning game 1 is P, and the probability of winning game 2 is P, then the probability of winning 2 games in a row is P times P, which is P squared. If teams are evenly matched, where each one has a 1/2 probability of winning, then the likelihood of winning 2 games in a row is 1/2 times 1/2, which is a quarter. Likelihood of losing 2 games in a row is symmetric, 1 minus P times 1 minus P. Again, if P is a half, then that's a quarter. Then the off-diagonal times are each P times 1 minus P. Now, all right, simple enough for 2 games, but what about 3 games in a row? Well, the notation we're doing on the previous slide gets a little cumbersome because now a 3-dimensional table is more difficult to visualize on a 2-dimensional screen. So you're not getting me in 3 dimensions. So instead, we're going to write it out. long-wise. 3 games in a row, what's the likelihood of winning 3 times in a row? That's P probability of winning the first time times P probability of winning the second time times P of winning the third time. That's P cubed. What's probability of win-win-loss? That's P times 1 minus P. With our assumption the teams don't get better or worse over the series, a loss in any of 3 games would still end up with 2 wins, 1 loss. So what's the likelihood the team wins the series, i.e. at least 2 out of 3 of those games? Just add up the probabilities in each of those 4 left-hand boxes. Again, add them up. So the probability of winning the series is P cubed plus 3, because there are 3 possible ways of getting P squared times 1 minus P. Then what's the probability the team loses the series? What's the probability of that? Well, just add them up again. So, what about 4 games or 5 games or 6 games or more? As you start to do the algebra, trust me, it's great fun, very exciting. You'd start to see those coefficients forming into what we remember as Pascal's triangle. Hopefully you remember that from algebra class. If I scale those coefficients by the total, then those are going to become the coefficients on the normal curve, which is actually the way the mathematicians figured out that draws from binomial distribution are going to converge to a normal distribution, because they figured out those coefficients, worked them out, figured formulas for how to represent those coefficients in Pascal's triangle. Pretty cool, huh?